Okay, let us start the lecture. I remind you that on the previous lecture we considered a flat pair of laws around a cylinder of the radius A and established the relation between this problem and the problem of construction of analytical function on a complex plane which should be analytical out of the circle of the radius A. And so this function, namely the derivative of the complex potential for incompressible ideal flow, gradient flow of the fluid, can be represented in the form of Lorentz series, which we write as follows. Here, alpha n are some complex constants, and z is a complex variable which has a standard representation in terms of x and y. So we can integrate this. This series is uniformly convergent in the domain out of the circle, and we can integrate it term by term and find the representation for the very complex potential. It can be written conveniently in the following form. So when we integrate this series term by term, the term with n is equal to 0 is an exceptional one. It is integrated to the logarithm. And as for the other terms, they are uniformly integrated. And we can represent the result of the integration in this form. In this sum, the term with n is equal to 0 is excluded. And here there is an additional term proportional to the logarithm. Here, alpha is a real constant. It was, it entered into the boundary condition, see in the previous lecture. And beta n are some complex constants, and lambda is also some complex constant. And of course, this constant beta n and alpha n and lambda are related to each other, but this relation will be irrelevant for us. So then we can find the real part of this complex potential by the standard means, and it can be written in the following form. I remind you that this complex variable can be represented in exponential form, in this form. Then we have this is for this series, and as for the term lambda times logarithm of z, its real part is reduces to the following form. I remind you that logarithm of z is equal to such an expression, and the following notation for the constant an and bn were introduced, namely beta n represented in the form form. So in fact, AN and BN are some real and imaginary parts of P10. And we can denote it in the following form for convenience. And so we need to find the derivative of this potential with respect to R in order to impose the boundary condition. In fact, we have already solved the Laplace equations for the vector field of velocity, but now we need to impose the boundary conditions on the circle or on the surface of the cylinder in 3 dimensions and at infinity in order to find these coefficients AN and BN, AN prime, and so on. So the derivative can be easily calculated. Is written as follows, and plus the term stemming from the logarithm. Then we impose the boundary conditions. First, we impose boundary conditions on the circle A, on the circle with the radius A. This derivative must be 0. Then we obtain the following system of equations. Solve it. The result is the real part of the complex potential is written in the following form. Now we need to impose the boundary conditions at special infinity, and these boundary conditions. Now we evaluate once again this derivative in order to impose this boundary condition. I write it for your convenience. And now we impose boundary condition at spatial infinity. That is when R tends to infinity. And this derivative must be equal to this expression. And so we have we just compared these two expressions and use the fact that cosine and sine function are independent with different arguments. And so we see that the only one term must survive in this expression, which is proportional to cosine. And then we obtain such a system of equations. And in fact, this is a solution of this condition. So now we substitute this to the general expression for phi, which we already obtained, and then we have all the constants entering this expression are known, and we have here one unknown constant which will be fixed from the other physical condition which will be imposed first. But now we have found the real part of the complex potential, but in order to find the velocity field, we need to find the whole complex potential. To this end, we may use this standard procedure of how to restore the imaginary part of analytical function when we know the real part. This procedure was described in the previous semester, and we can use it. Or we just have to solve the Cauchy-Riemann conditions. Cauchy-Riemann conditions in the cylindrical coordinate frame. They look as follows. In fact, these conditions can be regarded as a system of equation on the function psi. And one can easily solve this system, or I repeat that one can use the general formula which was obtained in the previous semester. Then the complex potential takes the form. And one can easily check that the real part of this potential does coincide with this function phi. So now we can find, in fact the problem is solved, and now we can find the velocity field. Remind you that given by such a derivative, and we need to take complex conjugate of this expression. The relation of the derivative is obvious. This is the final answer. In fact, one can simplify this expression to find the real and imaginary part by trivial. And but we consider, we must establish the physical meaning of this additional new constant of integration. To this end, we consider. Excuse me. I remind you that zero is such a quantity. It is a real quantity. It is the modulus of the velocity vector at infinity. Okay. In order to find, in order to establish the physical meaning of this constant, we consider such integral along the contour C, which encircles the disk. The picture. So disk. The center is the origin of the system of coordinates, and is the radius A, and C is some contour running in the positive direction around this disk. Then this integral is easy to evaluate by residues. For example, we must differentiate. In fact, this is the derivative of the function w, and these two terms give nothing to this integral because there are no terms proportional to 1 over z, and the only contribution comes from here, and it is equal to this expression. This. But we already gave the physical meaning of the real and imaginary parts of this expression in the previous lecture, and thus we see that circulation of the vector field V around along the contour C is equal to this constant, and the flux so the contour C is equal to 0 because this a real valued quantity, that is the imaginary part of this quantity, which is the flux of the vector field V through the contour C, is equal to 0. And this is an expectable result because this cylinder is impenetrable, and therefore the flux of the vector field V must be equal to 0 through the contour C. And as for this result, we see that the constant lambda double prime characterizes a circulation of the vector field V around the contour C, and it should be specified in order to determine the solution uniquely, this constant should be specified additionally. And so I write it, specified addition. Then we obtain a unique solution of our problem. In fact, the construction of the solution is finished. Now we consider the following problem. Namely, we consider a flat parallel floor around a plate, and but of course we can start from the beginning and using the same procedure in order to find the solution, but we can use a very useful trick, namely the conformal transformations, which we studied in the previous semester, in order to find the solution of the problem of flowing of incompressible fluid, either incompressible fluid around a plate, by simple substitution into this solution which we have already found. Okay, and in order to find this solution, such a solution, we need to find a conformal transformation which maps this cylinder, which in fact maps this cylinder into a plate. Or on a plane, this plate looks like a segment. And according to the principle of matching boundaries, if you find an analytical function which maps the boundary of this domain of analyticity of the function, which is here, to the boundary of analytical function, and this boundary is this segment, then this principle says that this analytical function realizes a conformal transform of this domain into this domain. Such some conformal domain, some conformal mapping. And our task is to first is to find such a conformal transformation, and the second is to check that the boundary conditions imposed here at infinity are preserved. Okay. Let us start with the construction of the conformal transformation. And at first, we introduce a notation. Convenient. Then the complex potential can be cast as the form. After that, we at first map the circle of the radius A into the circle of a unit radius. The analytical map, which realizes conformal mapping, is very simple. It's just denotation, such a denotation, and the inverse map looks as follows. And then W of xi is obviously okay. In fact, we have to check now that the boundary conditions are preserved, but we will check this fact only for the final conformal map, which is not constructed here. But when we construct the conformal mapping of this circle of a unit radius to such a segment. But it should be noticed that the boundary condition, the condition of impenetrability, that this circle is impenetrable for fluid, is preserved by any conformal transformation. In order to see that, we consider the following derivative. Which is just where z of L is a control C, characterize a control C. That is, we parameterize this control C by some parameter L, and the very control C is specified by this mapping. Then we can rewrite this derivative. The following form. Where tau x and tau y is a tangent vector to the control C. In fact, the derivative of z of L with respect to L is written in this form. That is, tau x is a real part of the derivative, and tau y is an imaginary part of this derivative. And it is obvious that such a vector is normal to the contour z of L, because it is orthogonal to this vector. One can check easily by taking this fact by taking the scalar product of these two vectors. And so we see that the condition of impenetrability can be written in such a form. And that is the imaginary part of this point must be zero. And it is clear from this expression that this expression is invariant with respect to change of coordinates. And so this condition is preserved by the conformal mappings. Thus, we do not need to check that our condition preserve our conformal mapping preserve the condition of impenetrability on the surface, which is the result of the mapping of the circle C, initial circle C. But as for the second boundary condition at infinity, we need to check it explicitly when we construct the conformal map. Now, the second step of our construction, the second conformal mapping, is complex plane psi, and here is complex plane Z. This complex plane Z is not the initial one, but in order for not to introduce additional notation, I denote it as the complex plane Z. And here we have such a segment as a unit circle, and we need to find an analytical map which maps the circle C into this segment. The answer is as follows. It should be noticed that while the problem of a floor, a flat parallel floor around a plate is an important problem. It is important because this plate is a simple model, the simplest model of an aircraft wing. And by using the conformal mapping technique, we can easily find velocity floor around such a wing. So let's continue the analytical calculations, and it is claimed that this mapping realizes the conformal mapping from this domain of analyticity into this domain of analyticity. In order to check this, one needs to consider the points xi lying on the boundary of analyticity, namely on this circle, and to verify that these points are mapped into the points of this segment. So, the points lying on the circle can be on the unit circle can be parameterized the following way. And when one substitutes this into this expression, one finds the following relation. Thus we see that indeed when phi runs from 0 to 2 pi along this circle, then the points z, plane, runs around this segment. I write it as somewhat bold in order to see this explicitly. And the inverse map, thus by the principle of matched boundaries, we have found a conformal map that we need. And the inverse map, one can easily find it from this expression by solving a quadratic equation. Here's the following solution. Here the square root is understood as a multivalued function, so one doesn't need to write here plus and minus, because these plus and minus are included into the definition of square root. And 1 over psi is written as well. So then one just have to substitute this psi into the expression for w, which is written here, and we will have the solution of our problem. At the end, we will have to check the boundary conditions at infinity. So w of z is given by the following expression. This expression can be simplified. The constant A, which in fact is an arbitrary constant, is an artifact of our construction, can be fixed from the boundary condition at infinity. Condition we have to consider such a derivative, and its asymptotics at infinity, and is equal to this expression, and we we impose the boundary condition that at infinity this derivative is a complex conjugate to the velocity field at infinity. I remind you that V has such a form, and the velocity field is obtained by differentiation of W, and then one needs to take a complex conjugate. Thus we need such a boundary condition, and so V is equal to 1/2. Thus we have obtained the complex potential and the solution of our problem. The velocity field is merely derivative of this potential with respect to z, which can be easily found, and then one needs to take complex conjugate. So we completely solve our problem. And okay, the next paragraph is called hyperbolic type equations. Hyperbolic type equations. In the previous section we considered the elliptic type equations, and I showed you several approaches how to solve these elliptic type equations and and we proved several general properties of the solutions of these equations. But now we turn to the hyperbolic type equations, and the first section, the subsection in this section, is a formulation of the Cauchy problem for such type equations. Here are some general words. We will not consider the general form of hyperbolic type equations, but we consider some particular case which is very instructive and shows the main properties, peculiarities of hyperbolic type equations. Then we will consider the wave equation in dimensions of space 1. Well, let's continue. So many hyperbolic type equations are written in the following form, in some system of coordinates. X are coordinates of space and belongs to R and T is time and it is greater than 0. Rho P are strongly greater than 0 and Q greater than 0 are some functions. And here the summation of repeated indices is understood. I runs from 1 to n, and we suppose that rho and q are continuous functions, and function e of x is a continuous function with its first derivative. That is, it belongs to C1, the class of functions C1. And then, let me denote this equation as 16.1. Then, this equation is of hyperbolic type and describes some oscillatory processes. The Cauchy problem is formulated as follows. One needs to find the function u depending on x and t that satisfies equation 16.1 for t larger than 0 and it obeys the boundary condition. In fact, this is our initially conditions, and in order to specify a unique solution to the Cauchy problem, one needs to impose the following initial condition. That is, one needs to specify the initial generalized coordinate, the function u, and the initial generalized velocity. The same as in classical mechanics. So, this is the formulation of the Cauchy problem, and we assume that f, which enters the right hand side of this expression, and u1 belongs to the class C0, that is the continuous, and u0 belongs to the class C1, that is u0 is continuous with its first derivative. And as for the elliptic type equations, the fundamental solution plays a crucial role in explicit construction of the solution of this problem. And so we will continue with at first with the construction of the fundamental solution for the equation 16.1, but in fact we will consider a simplified version of 16.1, namely the so-called wave equation, which is written as follows. We consider only the cases of 1, 2, and 3-dimensional spaces, but in fact the whole procedure that will be developed is easily generalized to the general case of an arbitrary n. And here, this box operator is given by the following expression. This is a Laplace operator, and this operator is called the D'Alembert operator. Or the wave operator, or the box operator, because of its notation. Here, A, the physical meaning of A is the velocity of propagation of perturbations described by this equation. And this equation, wave equation, is a particular case of partial differential equation with constant coefficients. And it is this fact that will allow us to solve this equation explicitly, to find the solution explicitly in terms of some integrals. And another remark is that this equation appears in many branches of physics. It describes, for example, the propagation of light in vacuum, or the propagation of sound in a video, or the propagation of perturbation on a string, on membranes, and so on and so forth. And in fact, almost arbitrary wave process with small amplitudes is described by wave equation. So it's a very important equation, and we will study its solutions. So the next paragraph is a fundamental solution of the wave operator. Another name for this fundamental solution is the Green's function. Retarded function, as we will see. Fundamental solution of the wave operator. So we consider the box operator. A is constant and we take it greater than 0. And then the definition. In fact, it is a particular case of the general definition of fundamental solution, which was given in the previous semester. Nevertheless, the fundamental solution solution of the Cauchy operator is a generalized function being an equation. The remark, in fact, as I have already said, this is a particularization of the general definition of fundamental solution to the case of wave operator. And what the remark is about the term generalized functions. In English literature, generalized functions are frequently called distributions. And these two notions are synonymous, in fact. So I will use these two terms interchangeably. Okay, here we know this equation, this definition of as 17.1, and in order to find the fundamental solution for the wave operator, one is just to solve this equation. And we will proceed with it. Take the Fourier transform of the left and right hand sides of this equation. We will take this Fourier transform only with respect to the variables x, and t is regarded as some constant parameter. So, for example, the delta function of t is constant can be taken off from the Fourier transform. Then denote Fourier transform of the fundamental solution with respect to variables x as e tilde st, where s the type of variables for three-dimensional space. And n is equal to 3, and this s is some vector. And now we use the properties of the Fourier transform, which we considered in the previous semester, and we studied the generalized functions, the distributions. Fourier transform, we find this equality follows from linearity of the Fourier transform. And as for this expression, since t is some constant parameter, and the Fourier transform t is taken with respect to the variables x, we can just take out the derivative with respect to t, and thus we obtain this expression. As for this Fourier transform, we used the properties of the Fourier transform of the derivative of some expression. These formulas were written in the previous semester. Then we find the form equation. This is already an ordinary differential equation with respect to the variable t. So the Fourier transform allowed us to transform the partial differential equation into an ordinary differential equation. And as for ordinary differential equation, we already considered their fundamental solutions in the previous semester in the corresponding sections. So here we just used those results. Then we see that tilde E is a fundamental solution of the operator of a harmonic oscillator, in fact. Here S is a fixed parameter. S squared is a fixed parameter. And this fundamental solution was found, and the answer is as follows. S, by definition, the modulus of the vector S. Then, in order to find the fundamental solution of the equation 16.1, or the wave equation, or the solution of the equation 17.1, one just needs to perform an inverse Fourier transform of this expression. And this sum of these Fourier transforms were calculated in our previous lectures in the previous semester, and I just write the final answer. And this Fourier transform, the explicit form of this inverse Fourier transform, depends on the dimension of space, and so there will be three different answers. General expression. Then we consider n is equal to 1, 2, and 3. As for n is equal to 1, the Fourier Fourier transform was found by us. It is equal to such a generalized function distribution. And then the fundamental solution in the case of one-dimensional space is written in the following form. As for n equal to 2, the inverse Fourier transform was also found in the lectures. And so we have the fundamental solution. And as for the case n is equal to 3, which of course is major importance, we have the following. Fourier transform reads as here delta as AT is a simple error on a sphere of the radius R is equal to AT. The radius AT and this simple layer can be rewritten in such a form as we showed in the previous semester. Then, in our case, we have the fundamental solution of three-dimensional space. Now we can simplify a little bit this expression. Here we see that the delta function with the complex argument enters this expression, and so we can rewrite it in simplified form. To this end, we have to consider such an equation. This expression can be written as follows, and one should bear in mind that R is greater than 0, and due to this theta function T is also larger than 0. Thus, we see that the only solution satisfying these requirements is R equal to A times T. Then we can rewrite this expression by using the formula for the delta function of complex argument. Various forms. Which will be convenient for us further. The mention should be made that this theta function can be omitted due to the fact that as long as r greater than 0, then t is greater than 0 due to this delta function, and so this theta function is equal to unity. And we omitted it here and write it in the following form. Definition. Such a fundamental solution is also referred to as the retarded Green's function. It describes, definition is finished, it describes the causal propagation of perturbations in accordance with to the wave equation. And the remark, causal propagation to the future, perturbation described by the wave equation. Remark. One can introduce such distribution E plus, which is equal to E defined above with reverse sign of t. And by using the above formulas, we can write it as the following form. It turns out that this function, this distribution, is also a solution to equation 17.1. This generalized function is called the advanced Green's function. It describes the evolution of perturbation into the past. Contrary to the retarded Green function, which describes the evolution of perturbation to the future. Okay. But of course, as for our problem, for the solution of the Cauchy problem, we need only the retarded unit function. And this is just a remark that you bear in mind. Okay, the next paragraph is about the retarded potentials. So in this paragraph, we construct the solution. We in fact construct the solution of the Cauchy problem, and in order to make this construction more transparent, we introduce the notion of retarded potentials, and the general solution of the Cauchy problem consists of the sum of two types of these retarded potentials. So we start with the first one. Potentials. That the distribution of x and t vanishes for t less than 0. And E dependent on x and t is a fundamental solution of the wave operator. Or B fundamental solution then the generalized function distribution V, which is by definition the convolution of E and F, is called the retarded potential with density F. The definition is finished. In accordance with the theorems which were proved in the previous semester, this retarded potential is a particular solution of the inhomogeneous wave equation. Because it satisfies this equation, of course, in a sense of distributions. And we will find in this section the explicit expression for this potential V. Under the assumption that function f, which is also called as a source. Is such that is equal to 0, and t is less than 0. The function f is called a source, and it describes sources and things which are present in the system. Okay, and we start with the case n is equal to 3. In this case, the fundamental solution has the following form. Then, let me number the formula. This one. This formula 18.3. Then from the formula 18.3, by using the definition of convolution for a generalized function, we have then we substitute the explicit expression for the fundamental solution. This delta function removes the integration over t prime, and we have then we take into account that this condition, that the function f satisfies this condition, and by using the condition we see that the integrand of this expression is not 0, in the domain where the whole inequality is satisfied. This quantity must be greater than 0, and so the points x prime, with respect to which the integration is performed, must belong to the ball with the center at the point x and the radius of at. We know this set of points as u x at. That is, it is a ball with a center at the point x and with a radius at. Then we can rewrite this expression. The following form. Here, minus means that it is the retarded potential. Okay, this is the final answer for the retarded potential in the case of three-dimensional space. Now we consider the case of two dimensions. Using the same formula, but with the fundamental solution for two-dimensional wave equation. We have fundamental solution written as follows. Then the retarded potential is the form. Function f. Now we take into account these theta functions, and the fact that they are zero when their argument is less than zero. This leads to the following inequalities. So we have this theta function and the condition that the function f is equal to 0 when t prime is less than 0 results in a change of the integration, the limits of integration here. And as for this condition, it means that the integration is performed in the domain which is a disk with a center at the point x prime and at the point x and radius a times t minus t prime. v times t minus t prime, and the center x, and the point x. As for the, okay, our lecture comes to the end. Let me finish. Thank you for your attention.